Hello and welcome. Today we're going to continue with some more properties of the determinant, starting with this corollary. The determinant mapping over a field F satisfies the following. 1. The determinant of a matrix changes sign if any two columns or rows are permuted. 2. The determinant of a matrix is 0 if the columns or rows are linearly dependent. 3. If a matrix A' arises from a matrix A by multiplying any row or column by some scalar A, then the determinant of A' is equal to A times the determinant of A. And finally, if a matrix A' arises from a matrix A by adding to one column a constant multiplicative of another column, or the corresponding operations on rows, then the determinant of A' is equal to the determinant of A. Let's prove these statements. Recall the determinant of A is defined as our multilinear function phi defined 2 videos ago, where applied to the columns of the matrix A. However, since the function phi is alternating, and the sign of the transition is -1, it follows the determinant of A changes sign whenever two columns of A are interchanged. Therefore, since the determinant of the transpose of A is equal to the determinant of A, it follows that what we've demonstrated also happens when two rows are interchanged. Next, let's consider if the columns of A are linearly dependent on one another. If this is true, then a multiple of one of the columns is in the span of the remaining columns. If we do it simplistically, then we have that A1 is in the span of the other 2 to n vectors. Then by linearity, we have f of A1 up to an is equal to f of this particular sum. Since we know that f is linear, so we apply it to A1 and we pull out the constants that make up A1. By 1, the function of f changes signs whenever columns 1 and j are interchanged. But if the two columns are equal, it must be the case that the function does not change signs. And I can know the case when the function f is 0. Next, we'll prove that if we multiply rows, then we scale up the determinant. And we see that since phi is multilinear, if you multiply any of the columns by A, then you can apply the multilinearity and you can pull out the A. And then since you have the transpose fact, then you do the same thing when any row is multiplied by A. Next, since the function phi is multilinear, we have phi of a row plus a constant times another row. We split it over that addition, and then pull out the constant, and we get this plus this term plus this term. But we know that the second term is going to be 0 since you have a repeat, and we proved that before, that if you have a repeat, then you get 0. All this is well and good, but it doesn't really give us an easy way of calculating the determinant of the matrix. One rather straightforward way of calculating it is by reducing the calculation to that of the determinant of smaller matrices. We write the basic formula of 1.69, which we'll recall has the following form. As expanding across the row, that is, determinant of A is the sum from j1 up to n of j2 up to jn equal 1 to n, so some permutation of j2 up to jn, times the sign of this. And then we sum for all j1. Well, this is just going to be equal to a11 times that new sum, which we will note is just almost the determinant of a smaller matrix in some sense. And then to that we also note that we have a11 was just aj11 since we're summing from j1 equals 1 to n. So we have to continue the sum. So we have a11 times this sum plus a21 times the same sum all the way up to an1 times that same sum. We'll note that this is simply the determinant of the matrix where the first row is where the row or the first row is deleted. This then gives us the determinant of A is a11 times the determinant of a11 minus a21 times this determinant, because note that we have a change of sign, because by deleting our thing we get a sign which has been permuted, so we get a minus sign there. Note that in this expansion, the expansion by minors, we see that aij is simply the matrix arising when the matrix A has rows I and j and column j deleted. For instance, we determine if a, b, c, d is equal to a times the determinant of d minus c times the determinant of b, but by our definition of multilinearity, we get the determinant of d is just d, so this is ad minus cb, the standard definition for a 2x2 matrix. And we can try this again by trying it with a 3x3 matrix. So we have 1, 2, 3, 4, 5, 6, 7, 0, 8, and we expand along the first column. So we get 1 times the determinant of this matrix, this 2x2 matrix here, minus 6 times the determinant of this 2 by 2 matrix here, plus 7 times the determinant of this upper matrix. And then calculating each of those using the previous rule, we get negative 105. Therefore, the columns of matrix A can be permuted with change of sign, and the same formula applies to rows since we can apply the transpose. This is a very easy approach to calculating determinants since you can usually just choose a row or column which has as many zeros as possible, so you have to calculate fewer determinants. Note that if the entries of AJ1 in our formula for 1.70 are replaced by AJI, then you have replacing column 1 by column I. So we get the result will be 0 because you have determinant of a matrix with two identical columns. Therefore, now let's construct a new matrix which we'll call A dagger, which is the matrix of entries Aij dagger is equal to negative 1 to I plus j, determinant of AJI, which is called the adjective matrix of A. And then it follows from our result from 1.70 that A times the adjective of A is equal to adjective of A times A is equal to determinant of A times I. For example, the adjective of ABCD is equal to D minus B minus CA, and then we'll recall that the determinant of ABCD is equal to AD minus BC. This then means that since we can apply this property, we get that we can solve AX equal to A by multiplying by the adjugate on the left and then dividing through by the determinant. That is, applying this identity on this equation so that we get X is equal to 1 over the determinant of A times the adjugate of A times the vector A. This is called Cramer's rule. With that, we've gotten some very interesting properties of determinant, and now we're going to consider some greater algebraic structures that matrices and lend to. We'll consider some other algebraic structures in which matrices occur. Thank you.